To Stony Brook last year. Before that, he had spent the majority of his career in the Midwest, University of Illinois, Urbana-Champaign. His academic training was he's a lifer at MIT. So he did his bachelor's, master's, and PhD in the electrical engineering department. Somehow both of us are underwater acousticians. But we are probably at the extreme ends in terms of he lives in an electrical engineering department, and I go to sea and have a lot of squishy things on deck. So it's a really diverse area.
Don't talk technical with us.
All right. But the most interesting thing, if people know about family trees, right? But we also have academic trees. So I was looking up Andy's academic tree. And his advisor at MIT is Alan Oppenheim, who, if anybody has ever done any signal processing, he wrote literally the textbook I used as an undergrad and most people have used for a long time. His academic great-grandfather is an MIT electrical engineer who started a little company called Bose. And then if you go back, his great-great-grandfather is Hilbert of the Hilbert transform, which may mean nothing to most of you, but if you're a math physics person, it's pretty freaking cool.
Skipped over Norbert Wiener.
I have them on here, but it's a Norbert Wiener, arguably invented the field of AI, certainly coined the term cybernetics. So that's a lot to live up to. So I'm excited. I'm excited about the seminar, and let's welcome them.
Excellent. Oh, we're turning down the lights now. It's really important. Okay, well, thanks for the invitation, Joe. And I just want to make sure those who are online can hear me, that my microphone is working. If there's some way to get an indication back that that's true.
Which room lights? It's the dial bulbs. Got it. It's time to be expanded. Keep going.
Okay.
I think just.
So I wanted to talk a little bit about my research as it overlaps with SoMAS. As Joe said, my training is in electrical and computer engineering, in particular signal processing and communication systems. One of the areas that I got introduced to right after my PhD, actually during my PhD work, was underwater acoustic signal processing in general, sonar systems, and underwater acoustic communication, so modems for things that are underwater. I worked for a small $900 million defense contractor in New Hampshire when I was a grad student, and then for a couple of years after finishing my PhD. And we built the first acoustic modems that were put on the Navy fleet based off of technology that was developed at Woods Hole Oceanographic Institution, where many of my colleagues from MIT were also appointed. And I found it to be just a fascinating and cool environment, a very challenging signal processing environment. And it just happened that after finishing up at Sanders, which became part of Lockheed, and it's now part of BAE, when I moved to Illinois, it was naturally easy to get grants from the Navy to continue working in that area. And for the last 30 years, I've been working generally in areas that also include underwater acoustics and communication systems. So I want to talk a little bit about acoustic communication systems generally, and some of the other places that we've been able to deploy the technology as it's evolved over the last 25 or 30 years. Obviously, I have to give a shout out to my graduate students. Most of them who are here are either still at Illinois or recently graduated, and at least one of them is coming to Stony Brook in the fall or in the spring. I'm hoping to try and get the second one to come as well, but we'll see. So I think it's important to look at history. Back in 1900, this is a diagram, very important diagram of a prognostication of what the French, I forget which magazine this was in, believed that the year 2000 would be like in the world. And they're really accurate, you know. We do play croquet at the bottom of the Long Island Sound, and there are many fish that interfere. I just thought it was fascinating that they sort of saw the 2/3 of the planet that are covered by water as a place that we would likely want to explore and inhabit. It's particularly interesting to think about how they projected we would do so. It involved things like inverse fishing, and of course, seahorses would become much larger and we could ride them. There would be races, and then there would be a bus that one could take from Central Campus to SoMAS that's driven by some local help. This is a real thing. It existed, and there are about 20 or 30 other diagrams like this, some of which are quite interesting about farming and aquaculture that are a bit more realistic. But I want to talk more generally about underwater acoustics, and not just underwater living and seahorse riding. As I mentioned, underwater acoustic communications was the area that I initially got exposure to this really challenging and interesting environment. And the Navy's been interested in acoustic communications for probably about 60 or 70 years, in large part because when you go underwater, the techniques and technologies that we use for communications don't work anymore. Radio frequency propagation, electromagnetic waves, don't propagate very well in water generally, or in seawater in particular. So acoustics are the means by which animals and fish and nature communicates in that environment. And there's a lot of opportunity to do so. Most of the work that the Navy has done has been for long-range sensing and long-range communication. So distances that are on the scales of kilometers to tens of kilometers. And as a result, because of absorption and other reasons, they tend to have been thinking about frequencies that will propagate over very long distances, and tended to look at very low data rate type solutions. Initially analog systems, and then in the 2000s or thereabouts, digital communication systems. And if any of you are old enough to remember voice band dial-up modem technology, essentially the Woods Hole micromodem that was developed based on Milica Stojanovich's PhD thesis, she is really, in my mind, the grandmother, I should never call her grandmother, the mother of acoustic communications. I really love the fact that prior to the publication of the central journal paper in her PhD thesis, 3 of the most prominent undersea acousticians in the world published a paper that said long-range coherent acoustic communications is not possible underwater, can't be done. And then her paper comes out and shows that it actually can be done, and they forgot that, oh, one can track phase, and we're thinking about discretization. There are a variety of reasons why her thesis worked, and a variety of reasons why these famous male acousticians argued that it couldn't happen, but she proved them wrong. I think it's great. Ever since then, people have been thinking about how do we do undersea communication better in more real time? How do we deal with the fact that sound propagates through water about 5 orders of magnitude more slowly than light or RF signals propagate through free space? So when we think about communication signals, you think about your cell phone, you think about radio communication, it's almost instantaneous from a transmitter to a receiver, and you can track things and you can track motion. Doppler on RF signals exists, but it's minuscule. But every 3rd grader knows that when a bus goes by or a train goes by, you can actually hear the compression and dilation of the sound waves as the object moves towards you and moves away from you. And if you're encoding information in the location, the temporal location, and the amplitude of an acoustic pressure signal, Doppler is going to be a big factor. And it's actually 5 orders of magnitude worse in undersea systems than it is in RF systems. So it's a really interesting and exciting area, lots of signal processing challenges, lots of estimation challenges. And one of the areas that I focused the last 25 years is looking at much wider bandwidths than the traditional modems that Woods Hole developed, and looking at shorter ranges where the 1500 meters per second isn't so long, doesn't intrude so much of a delay that the systems can't be practical in real time. I'll talk a little bit about how that led to some work in biological systems and through tissue acoustic communications, and some of the things that we learned about the acoustic nonlinearities in tissue, and we're able to see that those were giving rise to challenges in subsea broadband communication. Then I'll talk a little bit about some things we did in soils as well, because this is SoMAS. Other people that work in soils, you work in sediments, so you might be excited about it. Okay, So going back to that famous paper by the male acousticians, one of them is one of the co-authors of this paper, I won't point out who, but they also sort of categorized after Balitz's thesis, progress in undersea communication and recognized that if you multiply the distance of propagation by the data rate at which you'd like to achieve coherent communication, there seemed to be this sort of frontier that one could not get past. And it was largely due to the exponentially increasing rate of absorption or attenuation of sound with frequency as you go off in distance. So longer distances necessarily will have narrower frequencies that can propagate, and as a result will give rise to lower data rates. And over shorter distances, higher data rates are possible. So there's this range times rate being roughly bounded by about 40 kilometers per kilobit per second. And I've been really interested in this range where I've got much more acoustic bandwidth than many systems have been able to make use of. And the challenges cease to be attenuation and bandwidth limitation and start to become things like motion and Doppler oscillation. So for the engineers in the room, I'll go over just a quick review of what a modem looks like. And for those of you who aren't engineers, then you'll see a modem for the first time. You have a sensor, it's spitting out bits. This is data that is of interest to you. We typically encode that data using some form of forward error correction. So we put extra bits in there for redundancy so we can find errors and correct them. Then there's this process called symbol mapping, where we group together groups of these coded bits and turn them into a complex number on a plane. It'll just be dots on a picture board. We do that so that we can tell one from another, so that if I send this little dot, then I know it corresponds to, in this case, I can't read it, but let's say 0000. And if I receive that and I equalize that dot back, I can pull that off and say that's 0000. That's 4 bits at a time. Then I want to modulate that onto a waveform that can then be introduced into the world. So mathematically, that just corresponds to multiplying this complex number by some waveform shape and then clocking them out over time. We then will modulate that up onto a carrier. Acoustically, this will be somewhere in the, let's say, hundreds of hertz to tens of kilohertz or even megahertz type frequency range. And then this signal is introduced into the real world through a transducer in this case. The signal will propagate through the environment. We model this as happening through a linear time varying process. Anything is linear if you look over a narrow enough region of amplitude and time, and as long as you let it to be time varying, we capture that. Then at the receiver, we sample the signal, make it a discrete time, we bandpass filter to get the frequencies of interest, we demodulate it down to baseband, we low pass filter it, and we get a jumbled mess that doesn't look like what we transmitted. But the good news is that if we can estimate and track this linear time varying process, we can equalize that back out to get those symbols that were transmitted. We can then demap them into bit sequences. We can decode them to correct any errors. And whatever we learn about those errors, we can use to adjust our equalizer in an adaptive way. And then we've got the data back. So now you're all communications engineers. You can all build a digital acoustic modem. So as I mentioned, most systems that the Navy has been pursuing and commercial modems that you can buy today don't look very different from a voice band dial-up modem from the 1980s. And if you're not old enough to know what a voice band dial-up modem is, we used to communicate to what is now the internet by taking our telephone receiver, which was a handheld thing that was connected by a curly cord that would always get tangled, and we put it onto a microphone and a speaker, and then it would dial some number, and then you'd hear D, and that D was the acquisition process and synchronization of the transmitter and receiver, and then you'd hear shh, which was basically a broadband acoustic signal that was basically implementing what I just showed you. If we've got a lot more bandwidth than a couple of kilohertz that a voice band modem uses, let's say we've got hundreds of kilohertz available, then we can do a lot more. We can start to implement very aggressive digital signal processing algorithms into devices that can be very small and low power, and do a variety of signal processing tricks to get data rates that were unheard of in previous generations, even other than the company that I started about 10 years ago, commercial modems that can achieve that. And then a question sort of arose, well, what would you do with more bandwidth if you could make it? So if you could go from a kilobit per second to a megabit per second or 10 megabits per second, what would you do with that? And one of the first questions we asked was, well, could we send video over processes that had substantial motion? Could we detect, estimate, and then undo the effects of Doppler to be able to coherently and consistently transmit video? So we started in a wave tank, which we have wave tanks at Stony Brook. We have wave tanks, so not unlike one that you have. And here what you're seeing is I've got an acoustic transmitter, an acoustic receiver. There's a video camera that's sitting right here. It's taking the video that you were watching, and it is digitizing it and sending it through that same stream that you saw before. It's transmitting it from one, receiving it the other, and the transducers are moving back and forth with respect to one another. And we were able to, without dropping any packets, completely recover and transmit the video. No one had ever done that before. And at first, people didn't believe that that even made sense or that it was possible. So we needed to show them that you could do it from a real system deployed from a boat. I believe we have boats in SoMAS, so there's an acoustic modem that we're deploying from the surface. And there's a little vehicle that currently is sold with a big long tether on it that's got fiber optic control and power. And what you're seeing here is video from the camera that's on the front of that vehicle that's sent acoustically from the vehicle to that topside modem, and it's streamed along. So this type of live video transmission needs a couple of hundred kilobits to a megabit per second of acoustic bandwidth, but it's achievable. We build them, we sell them, we can do it today. This is a whole new set of applications that are available for tetherless, autonomous, or remotely controlled vehicles subsea. So that was fun. And the next question that we had was, well, if we can do a megabit per second, can I do 100 megabits per second? Can I do a gigabit per second? I'm an engineer and I like challenges. So one of the things we wanted to sort of ask was, could we do a hero experiment? If I wanted to see what is the fundamental limit for acoustically transmitting data from one point to another, what could be said? So this is, really cheap, right? I got a transducer right here that's sending in this particular picture, it is a 20 megahertz bandwidth signal. And I've got a needle hydrophone, and I'm sending. So remember those little dots that I said? Well, here I'm sending 64 of them. So I'm grouping together more bits per symbol and transmitting them from one to the other, and then running this little equalizer. And in this experiment, we got 120 megabits per second, and with a pair of matched 80 megahertz transducers, we got up to 350 megabits per second over distances that were, only a couple of centimeters. But it was something that had never been done before, and people didn't think was possible. Why did we do it? Well, because we wanted to see if it was possible. We wanted to ask the question, are there applications where today, either we don't send data because we don't have RF transmission, or we use RF because we think it's the only thing that will work, when naturally something that couples better to the medium can also do as well. And a natural collaboration ensued between my research group and one of my colleagues in biomedical ultrasound. He was interested in implanted biomedical devices, being able to communicate with them, being able to push data onto them. Maybe it's a software update to an artificial organ. Maybe there's a sensor that's collecting data. A patient goes into the hospital. I don't know if you've seen anyone that has had to do this, but you see someone come home from the hospital, they've got this little recording device that they have to wear for a week. And it's transmitting over an extremely low data rate from something that's inside them to this coupled RF receiver. And after a week of wearing it, they then bring it back in, and the doctor will then download it onto their system, and she'll look at the data and sort of see, okay, we have to operate or we don't have to operate. But all of that had to happen through a very slow and convoluted path. And if we could access the device immediately in the office with an ultrasound, pull off megabits of data, maybe upload new calibration or new software, that could all be done. We even thought about surgical robots implanted in humans. What could one do? So one of my students worked on a piece of her PhD thesis was looking at through tissue communications. We developed a couple of experiments just to see, again, what was possible. And it's much easier and requires much less approval to send data through store-bought pork chops and a beef liver than it is to do this through live animals or dead animals. So the first thing we did was we literally got meat from the store and put it in the ultrasound lab and went through the same process and got very nice results and developed a megabit per second experimental acoustic through tissue communications. I'm a big fan of acronyms as opposed to initialisms. Initialisms are just a bunch of letters that you read together like IRS. But this is MECOMS, and MECOMS really tells you what it is. And we presented this at a conference in Europe, and it was amazing how many people got excited about the prospect of doing this. Instantly, we saw proposals from around the world for new postdoc positions to explore what can be done in this field. So we were excited that that this got some uptake. It also landed me in the Journal of Improbable Research. The article was translated into many different languages, and I got phone calls from strange radio stations in other countries asking me about MECOMS. I think Netflix and Grill was applied to this as well, because we talked about being able to send data in some of these experiments, essentially at the data rate that would be required for sending Netflix. So that led to thinking more seriously about what could we do with implanted medical devices or surgical devices. My colleague in biomedical ultrasound works a lot with rabbit models. And when he first told me about rabbit models, I thought, oh, it's a model of a rabbit. That's nice and fuzzy and cute. And I'm okay with us doing that. It would be fun. And then I saw what they did to the rabbit, and I decided that I would let him and the veterinarian take care of that piece of the research. I didn't want to be in the room, but this is a rabbit. This particular example was an in vivo experiment, which meant that in this particular case, first they worked with euthanized rabbits. So these were some actual rabbits that had other experiments that they had taken part in. And then the rabbit participated in acoustic experiments afterwards. We then did some experiments with some anesthetized rabbits and needed to show that the types of transducers we wanted to use were biocompatible, that the data was not perturbed by motion, breathing, heart rate, blood flow, and that we'd still get good performance. And what you see here is this is the mean squared error versus time. So these are numbers of signals that are transmitted. It's a typical learning curve for an acoustic modem, just showing you that low means good, and initially when it starts, it doesn't know what it's doing, and it burns the acoustic time rate acoustic channel, and it maintains a mean squared error that's low enough to be able to decode all of these. This is 128 QAM, so there's 128 little dots that we're using to encode pieces of digital information. And this was also exciting that this was possible. So we thought, well, NIH should probably want to fund this so we could do things in humans. And I didn't like the idea of animals being destroyed in experiments. So we did also have access to, and this is something I had remembered from my childhood growing up in Illinois. There are cows at the University of Illinois that have this little portal that goes into one of their many stomachs, and you can reach in and you can have access to the rumen and you can sort of see the decomposition. And anyway, if you live near an agriculture school, like Shep, you probably had these in Purdue. They probably had big like P on them or something for Purdue. Ours didn't. This is Lena, and Lena was happy to take. This is Lena. This is Zen. Zen was one of my PhD students who worked with Lena on this particular experiment where we wanted to show that we could do some communication through the GI tract of a live cow that took part in the experiment. She was awake and she was happy. She didn't need any drugs for this. And we didn't have to do anything other than thank her after the experiment. So this was acoustic communication, which this portal is a fistula that they put into the cow. So this is a fistulated or a fenestrated cow. So that led to us wanting to pursue human trials for things like wireless capsule endoscopy. So around 2000, a researcher in Israel came up with this idea of a pill that could have a little chip on it that had both a camera for taking images and a small RF transmitter for sending those images outside of a human, and then you could swallow this pill, and pictures could be taken about 1 picture per second or so as the pill makes its way through the GI tract. I don't need to get into the details, but there are certain parts of the anatomy that are more difficult to access without open surgery. You can go with a scope from the top and you can go from other means, but there are parts in the middle that are difficult to get access to. And this wireless capsule endoscope was revolutionary. In order to get it to actually happen, though, the team had to start a company and just build it and do it, because they couldn't get funding to do the research around it, because nobody believed that it would be important, or nobody believed that it would make a difference or that it would work or whatever. But now these are done all the time. And here at Stony Brook, I believe our GI team does a couple of hundred of these wireless capsule endoscopies per month. So we wanted to see, could we do this acoustically, and could we do better than 1 still picture per minute and have someone have to walk around with this little pack that's getting those images transmitted from one to the other. The initial NIH proposal that we put in, they told us, yeah, this will never work. You need to show us that you can do it through intestines. Well, we showed we've done it in rabbits and in cows and in pork chops and in beef liver. What more can you want? But when you get NIH reviews, you do what they say. So at the University of Illinois, we had access to the meat science laboratory. I always wondered what they did at the meat science laboratory, and well, they do meat science. I went into the meat sales room to get access to porcine intestines, or either intestines of pigs that are slaughtered at the ag school. And I had to sign something that said I would not eat them, because they weren't allowed to sell them to me if I wanted to eat them. And I promised them there's no way in the world that I will eat these things. So we set up a little experiment where we had these sound microcrystal. These are about a 1 megahertz center frequency and about almost 100% bandwidth, so about a megahertz of bandwidth. A little resonant piezoelectric crystal on the outside, and to sort of emulate going through the tissue and skin, and then have access. We wrapped it, of course, in bacon, and then use some coupling gel, and then we put inside, we filled it with fluid, and then inside put our camera and another transmitter to show that we could essentially replicate what an experiment would be like if one were a pig and were to swallow one of these capsules. And we were able to show a real-time, let's see if it plays, show a real-time setup where we can take images and we can transmit them from inside the intestine to outside the intestine. And here we're just limited by the probe of the camera that we're using didn't have a really great lens. But essentially we're able to show that we could grab the data, we could transmit it, it can make its way through, and we could do exactly what NIH had asked us to do and show that it would work in these kinds of models. And of course, the reviews from NIH were, oh, your images don't look very good. Again, I'm not trying to sell a camera or invent a camera, I'm showing a new technology for transmitting information. But in any event, that's where we were at the time there. So we learned a lot from working with ultrasound acousticians, and typically in biomedical ultrasound, the bandwidths are much wider than we had ever used for ocean acoustic signal processing, ocean propagation, and the amplitudes of the signals divided by the distances or the scales over which we were transmitting were also much higher. So the wave equation through which acoustic pressure waves propagate is nonlinear, which you all probably know because you're in SoMAS. But in the ocean acoustic signal processing world, we typically use a linear model because we're talking about much narrower bandwidths, much lower frequencies, and much longer distances. But in some of those hero experiments that we had tried to get to a gigabit per second, we saw that it wasn't signal to noise ratio or estimation performance that was limiting us. It was interference from acoustic nonlinearity. And being an engineer, I and my students thought that the nonlinearity was in the power amplifier. I thought we were just saturating the signal. We were introducing it artificially, but of course my colleague in biomedical ultrasound said, no. The water itself is nonlinear. There's a nonlinear component to the wave equation. And as the signal propagates, it's building up nonlinearity, and that's what you have to deal with. And I thought that was fascinating. Of course, it's obvious to him and probably to all of you, but it wasn't at all obvious to my community. And so when you push the math sort of through, what this acoustic nonlinearity will do to a communication signal, you essentially get, in the absence of multipath and bandwidth limitation, you get some additional intermodulation of the signal that's going to distort it. And for narrowband signals, it's not a problem because these harmonics show way out of band and you just filter them out. But for broadband acoustic communication signals, they're a problem. So just simple example here, I'm showing frequency versus amplitude for a narrowband communication signal. Narrowband meaning the bandwidth of the signal that I'm trying to transmit is narrower than about 2/3 of the carrier frequency. So if I'm sitting at, let's say this is a megahertz, then the bandwidth of my transmitted signal is narrower than 600 kilohertz, in this case, much less. So the signal that I transmit introduces these harmonic components, these distortion products, which over longer distances and narrower bandwidths, you don't see. But if you're trying to really push the limit of the performance of these systems, you immediately induce intermodulation that distorts the signal in band. That was eye-opening. It's obvious in hindsight, but again, none of the people in the underwater acoustic communications world had really thought about this before. So we wanted to see what happens specifically to communication signals over small scales, like in tissue, like in the rabbits and cows and humans that we're thinking about, and over longer scales. And we were able to show that absolutely. So here, this is a sort of standard type of graph that one will look at communications engineer. You'll ask, as I increase the signal to noise ratios, I put more energy into the system, how does the bit error rate behave? So high is bad and low is good. You want low error rate, meaning your data goes through without errors. And if the effective bandwidth of your system was less than 50%, so you were occupying less than 50% of the center frequency, the system behaves more or less as one would expect for a linear system. But as soon as you get above about 70% effective bandwidth, you get all this intermodulation and it gives rise to an error floor. So the systems just won't work. And no amount of increased signal strength will help you. It actually makes it worse. So we wanted to then look more carefully at the subsea systems that we were trying to deploy over distances of, let's say, 10 to 100 meters with bandwidths of 100 to 100 kilohertz up to a megahertz. Are these kinds of intermodulations present, and do I need to worry about them? And I guess what's worth gleaning from this set of slides is if we assume that the world is linear and we transmit so this is time versus frequency at a distance of 50 meters, 10 meters, and 1 meter from the transmitter. If we assume that the world is linear, we don't excite frequencies outside the bandwidth that we're occupying, and everything is good. And in the real world, which is not linear, we actually excite all of these harmonic components, which then can come in and distort the signal. And that second fundamental, or the second harmonic, actually builds as the signal propagates through the water up to a distance at which the energy level is low enough and enough absorption has happened that it's no longer inducing nonlinearity. But all the damage is done kind of in the first couple of meters of transmission. And then after that, so in this case, after about 10 meters of transmission, there's no more energy being pumped into that harmonic, but it's already there and it's already distorted your signal. So we explored this over practical distances and wanted to sort of think about why don't we see this in some of the acoustic communications experiments that have been done historically. And the answer is just that we have not been trying to put enough bandwidth into these systems. But the kinds of modems that my company makes, those megabit per second, a couple hundred kilohertz modems, actually do excite this kind of second harmonic. Okay, so after we explored sending signals through the ocean and sending signals through pork chops and beef liver and cows, I had a colleague in civil and environmental engineering who was particularly interested in through soil communication techniques that didn't require radio frequency transmissions. how am I doing on time? Am I?
You're good.
I keep
Yeah.
looking at the
36.
clock in the back, and I'm not sure if it's moving.
36.
Okay, good.
Correct.
So, colleague who's a geotechnical engineer, and he told me that any major construction project, in particular in a big city, like let's say you want to take down a building that's currently a parking garage in Manhattan, and you'd like to put in, I don't know, a 70-story high rise, and put your name on there in big gold letters. How do you do that without having the buildings around you affected and toppled? In fact, you probably saw in the news recently, there was a group that had built a tunnel in Brooklyn or in Queens or somewhere from one building to another, you know, I don't know if they're using spoons or whatever it was, but they sort of dug a tunnel on their own beneath a bunch of buildings. And then people were wondering, well, why is that a problem? You know, it's just, they're just digging, it's just plain. Well, the answer is, when you disturb I need to tell you, you're in SoMAS, but so when you disturb the soil substructure, you're changing all kinds of statics and dynamics that are possible, or that are supporting the surrounding infrastructure. And if you're a civil environmental engineer, you're going to go build something in Manhattan. The first thing you do before you do anything else is you install many boreholes all around the prospective site for the excavation. And in the borehole, you'll insert a number of inclinometers and piezometers and various sensors to be able to tell if over the duration of this project, things are shifting or pressures are changing, or water inlet is changing. And they'll put hundreds of these around a site. And these simple little sensors will then be tied by a wire that will come up, you know, maybe tens or hundreds of meters from below ground in these boreholes to a surface cap where there will be an RF transmitter, there'll be a radio, and they'll all connect together to probably, you know, Winnebago, or, you know, a little box office that's on the corner where someone is just monitoring the job site to ensure that things are okay. The problem is that about half of the wires foul over time. So they'll put in a couple of hundred of these sensors, and by the time the job is done, they'd be lucky if they have maybe 50 or 75 of them left. So he wanted to know, are there other ways that we can send signals to and from these sensors that are below ground, other than running a wire from below ground all the way to the surface? Of course, I thought, well, how about acoustically? And we were motivated by the fact that dolphins and kangaroo rats and elephants and many other animal species communicate through soil acoustically. They're not sending high data rate, but they are sending signals. And certain types of soil will transmit acoustic waves very well, and others won't. But we wanted to understand what was possible in, you know, these kinds of environments where there was sand and clay and both very dry and very porous materials. So we set some graduate students at the project. We came up with some relatively straightforward modeling of the multipath propagation through layered media, and, you know, set it up and says it looks a lot like underwater acoustic communications, except it's going to be different velocities and different types of media. So the sound speed profile will be different and the absorption profile will be different, but we can apply the same kinds of tools. One of the challenges that my students overcame was we didn't really have good transducers for inducing pressure waves into the soil. They tried a variety of things, including if you've ever had a couch at home that you wanted to put a subwoofer on, there's something called a butt kicker that you screw to the back legs of your couch and it vibrates the couch. So we encapsulated a butt kicker into a waterproof housing. But in the end, they built this little transducer with very low power. It was essentially a clipper that induced an on-off keyed impulsive train into the soil. The received technology is very similar to what we had for the underwater acoustic signals. And here they are out on my farm in central Illinois. You can tell it's central Illinois because if you take the derivative of the spatial plane with respect to space, you get zero everywhere. I think in Illinois we get like 7 or 8 zero derivatives. I don't know what it is in produced area, but it's pretty flat. So we did a number of experiments, sending acoustic data over a variety of distances, and showed that we could get a few bits per second over tens or even here I'm showing up to 35 meters, but we were able to get up to about 50 meters of propagation acoustically with these little home-built transducers, basically showing that it was possible, and that we got the same kinds of challenges in terms of a multipath environment, but there's no Doppler because nothing's really moving here. So in summary, I've been looking at a variety of things in my career. One of the threads has been acoustic communications. I'm particularly interested in challenging environments or interesting environments. We've looked at subsea, through tissue and through soil environments. And in all of these cases, taking in some of your domain knowledge, your knowledge of what the underlying physics and material properties are, will dramatically improve the performance. It offers opportunities for collaborating with people that really understand the media and the application. And it gives your students new and meaningful experiences that they probably wouldn't get anywhere else. And that's what it looks like in Central Illinois in the summer as you're digging holes for acoustic communications.
Thanks, Andy. We'll open the floor to questions. I'm actually gonna jump in with, oh, Thomas, you wanna go? Go ahead.
So, thank you very much for interesting talk. I want to go to the section where you had a transmitter going through, I think it was the meat part. There was a term, Janus, and the way I understood Janus is looking back and forward in acoustics. I didn't quite see the connect. Why would you need that? Maybe the only thing I can think of is implanted.
Okay, let me go back to that slide. So I think you were talking about.
No, I think it's forward. I think it was the
Here?
bags of meat after this. There,
Yeah, I
Yeah.
think that one.
Okay,
right?
and what was the question about this? Or was it not about this?
There was a term, there was a term on the slide, Janus.
Oh, Janus. Okay, yes, okay. So Janus, about 10 years ago, when a number of companies started trying to make acoustic modems, underwater acoustic modems, one of the challenges in any communication platform is interoperability. So, your cell phone would be useless if you could only talk to people who had a cell phone that had the same carrier in your same hometown on the same frequency band. And if you can't talk from an iPhone to, a Samsung, it's useless. So Janus was a protocol that was developed by NATO countries for interoperability between underwater acoustic modems. It's a low data rate, frequency shift keyed modem protocol. And the goal behind Janus was just to say, can we agree that if you make an acoustic modem, you'll at least have a 80 bit per second Janus compliant protocol where my fishing net and your unmanned undersea vehicle and your meat comms modem can all talk to one another efficiently. It's like a fax protocol, but for acoustic modems. Yeah. Sorry.
So I have a question. So obviously an acoustic modem is great because it can transmit information from an instrument. We actually use them when we do deep net tows to get the depth of the net so we don't run it into the bottom. But your time varying correction factor is essentially tomographic information, right? So can you just talk about, has anybody tried to do that? And tomography is like, I send out an acoustic signal, I look at how it's different from what I transmitted and I get information about ocean temperature or ocean density variations. Has anybody tried to do that over the shorter distances that your modems operate at?
Yes, and your instincts are spot on. So, is anyone familiar with the ATOC experiments, acoustic thermometry of ocean
Ocean climate,
climate?
yeah.
So this
I-
was maybe back when you were in graduate school.
The news, I went down to visit Scripps as a college senior, came back, front page story in the LA Times was the first big hit on ATOC. Yeah.
So it's just last year.
Yeah.
So the idea behind ATOC was Art Baggerower, who is a well-known acoustician and ocean scientist at MIT. He and colleagues at Scripps wanted to look at whether global warming could be measured by integration of the Earth's temperature through the oceans. So we knew at the time that global warming was measurable and real in cities and in places where humans live. We could put instruments and measure them and see that over time, temperatures in cities had risen. But what we didn't have was concrete data that the oceans were actually themselves rising in temperature and that they were rising in aggregate across the whole ocean, not just in the harbor nearby a big city. So they put a transducer. They did a couple different experiments. One of them was they put a very large transducer in Heard Island, which was in the Indian Ocean, and played an acoustic communication signal, very low frequency, and induced it into what's called the SOFAR channel. So what's really cool about ocean acoustics is sound speed is a function of salinity, temperature, and pressure. And the ocean is warmer near the top because the sun heats it up, and it's cooler down deeper because there's no sun, and the pressure increases as you get deeper. So you get sound speeds that are fast near the surface. They slow down a bit as the ocean cools, and then they speed up again as you get deeper because of the pressure. So you get this natural curve, and that serves as a waveguide. So sound that's induced into that waveguide will sort of stay in that waveguide for millions of meters, literally millions of meters. So they did acoustic communications over megameter scales from the Indian Ocean to the California coast, into the Japan Sea,
Washington,
to the
Alaska,
Atlantic coast, basically all over the planet. And the goal was, if we can measure the time of arrival, the time of flight, then we can get out the average velocity of propagation as essentially the integral of that sound speed profile over all of the paths from source to receiver. So that was a form of tomography, right? They're taking a tomographic measurement, integrating over megameter scales for climate change. And guess what? The Earth is warming. Anyway, it was big news, but that data was really cool because they were able to see all kinds of multimodal structure that remained coherent for millions of meters, literally from the Indian Ocean to the coast of California. It's actually absolutely astounding. And it's no wonder then that, whales and dolphins and other animals can communicate over vast distances by just inducing those sounds into the SOFAR channel and letting them propagate. So at shorter scales, one of my most recent PhD students looked at, if I have an unmanned underwater vehicle and it's communicating via an acoustic modem to, let's say, a top float or top buoy, can I use the tracking of the acoustic of the acoustic path from source to receiver to infer something about the position of the vehicle? So typically an unmanned underwater vehicle is kind of like a Roomba. They sort of launch them and they can sort of go in long, they try to go in straight lines using gyros, but without any feedback, they get a little bit off course, but they kind of go back and forth and back and forth. They mow the lawn and they come back up to the surface to get a GPS log to figure out, am I even close to where I was? And then they can correct the path based on where they now are. We wanted to know how long could one go without a GPS log if you just had an acoustic comms log. And it turns out that it works really well, especially if you're over distances that are tens or hundreds of meters, where the direct path is resolvable. So I can look at path length variation coupled with rate gyros and other components, integrate those into the internal inertial tracking software and do much better. It's very cool. And the upshot of that is if you have an acoustic communication link with an unmanned autonomous vehicle, you can essentially use it for tomography and geolocation. Cool. Jeff.
So I'm sitting here thinking about ice. There's a lot of interest in ice in various forms, glacier ice, sea ice, and so on. And it's usually hostile environments, difficult to get to. And I'm just sort of fantasizing about, thinking about, could you place a sensor in, you know, a glacier that is accumulating snow, losing it and measure very simple variables, temperature, salinity, motion. And then could you have a high enough data rate that you could send a drone to do the data transmission? So has anyone tried acoustic communication through ice, and am I having crazy thoughts here?
No, not crazy thoughts. So there's a lot of work in the Arctic and the Antarctic. And, you know, for a long time, there was a military significance to being able to go under sea ice and explore. It's difficult to have a tethered vehicle that goes under sea ice. But a lot of people do things like put geophones and hydrophones either in ice, on ice, or under ice and listen to it melt, listen to it crack. And they'll use acoustic modems to send the data. They'll use unmanned underwater vehicles to go and try and retrieve the data. They're not yet using the megabit per second modems, but they are using acoustic modems to send data back and forth. So it absolutely is an area. And there's a lot of folks that are in sort of the spaces that Joe and I live in, the underwater acoustics world, and in particular the communications world, where that's a big interest. Cool. One of my colleagues right now, who's a collaborator on this, is down on one of those very long expeditions where we can't talk to him for a couple of months.
I'm wondering what the altitude limitations of using acoustic signal transfer,
You mean the depth?
height in the atmosphere.
Oh, height in the atmosphere.
At what point do you lose transmission capability?
So I'm a little bit confused. So you want to do acoustic communication through air, or you want to go from water to air, or what do you want to do?
How high in the atmosphere can you use acoustic transmission?
Well,
How far into space? Put it another way.
so I don't know why you would, because outside of water, RF works, and it can go for,
It was just a curiosity question.
yeah, so,
Not why you would want to do it, but I'm
Right.
curious.
so I don't know. I do know that acoustic communication through air is of interest for certain applications where either you don't have control over the RF environment, or you just have no idea what the protocol is that are being used. So for a while, I don't know if it's still the case, but for a while, TV manufacturers, printer manufacturers, and other home electronics wanted to do protocol synchronization using ultrasound in your home, because your cell phone has a speaker and a microphone that can hear above you. It can play and hear above human hearing, so it can emit and receive signals that won't bother you. It'll bother your cats and your dogs, but they didn't care. So you're either a computer or a cell phone could talk to your TV and do some synchronization without you needing to go and select the Wi-Fi channel that corresponds to the TV. Also, if it could be done all acoustically, and the TV only had to have a microphone and a speaker and not a Wi-Fi chip or a Bluetooth chip, it also was free and somewhat protocol agnostic. So in room and in air, I'm aware of. I don't know anyone that has looked in the upper atmosphere. As of course, as the air gets thinner, it's more difficult to propagate acoustic pressure waves in space. Nobody will hear you scream.
Right. So, I mean, so like you go and you Star Wars and you have all the sound effects of, the Imperial war cruisers in space. And obviously that's not correct.
That's right. I've been on Imperial cruisers and they're very silent. A friend of mine has a new electric vehicle that's silent, so there's an expensive package that they charged him for and added to his car. So that when he drives at slower speeds, it makes vroom kind of noises, so that it sounds aggressive inside the car, so you can feel good about it. But then also outside the car, it played celestial kinds of sounds, so you didn't accidentally run over the gardener or grandma or something. It's interesting. So maybe the Imperial Sound Trooper are special effects that are just in your own mind.
So I think we'll wrap up there. Please join us over in the Swanson room for lunch afterwards or for more questions. And let's thank Andy once again.